In this lesson, we're going to go over complex numbers. So if you've not watched our first video on complex numbers, I would advise you check it out. Check the tag there. Okay, so in this video, basically, we're going to go over the moivre theorem and also get to look at the conversions from rectangular form to polar form of complex numbers. So I've got quite a number of questions and also the basics that I'm going to cover in this video. So if you are taking favored complex numbers, I would advise you watch the entire video to get more understanding of the concepts. Alright, let's start. Plot the following complex numbers in the complex plane. So how do you get to plot a complex number? So the way we get to do it is we have to understand that the actual xy plane that we know, we're just going to change something about it. The y-axis actually gets to become the imaginary part. Then the x-axis basically becomes the real part. And remember, from the start of complex numbers, we say that when you have a plus ib, the part attached to I is basically what we refer to as the imaginary part. Then the part without I is basically the real part. So looking at the first complex number, we have got -2 plus I. So if you look at the real part, it's basically a negative. So where do we expect the negative to be on the x-axis? Obviously to be on the left. So then I is a single unit on the y-axis. Okay. So basically this complex number is somewhere there on the complex plane. Okay, we've plotted it. The second one says 1 minus 3i. Okay, so where is 1? On the x-axis, basically somewhere this side. Then -3i is supposed to be down somewhere there. So it's supposed to be somewhere there. Then the last one, the root of the root of 3i. Okay, the root of 3. So basically this tells you that you don't have a real part. So the real part is 0. So it means that you're going to be along the x-axis, basically along the y-axis, because that's where we expect our x to be 0. So if we are that, a third root is supposed to be basically a number that is greater than a 1. So obviously somewhere straight tree higher there. That's basically a point we're going to have it. So assuming that is like a root of 3i. So we've plotted all the complex numbers, and that's how you get to go about it. So if you know how to plot a complex number, this is going to be very applicable as you get to transition to what we call the polar form. Okay. So another concept that we've talked about is the issue of dealing with the absolute value. So we said if you have a complex number in the form of a plus ib, you get to determine the absolute value by basically saying the absolute value of such a complex number, assuming that is basically our z in this case. Our absolute value of that complex number would be the roots of a squared plus b squared. So let me just write that better. So what we're saying is our z, the absolute value is going to be the roots of a squared plus b squared, so the root of that. So that is how you get to find the absolute value. Okay, so looking at that three concept that we have in mind, what complex number have we been given in this case? So if you look at our work, what we have our complex number is basically -2 roots of 3 minus I. So that is our a, and that is our b. So our b is basically the coefficient of I. So therefore in this case our a is -2 root of 3, then our b is -1. So from the basic concept where we are saying the absolute value is basically going to be a squared plus b squared, then the square root of that. Okay, so let's try to move on. So what we're going to have is our a is -2 root of 3 squared plus our b is -1 squared, so the root of that. Okay, I don't know, let me try to do that better. I can. Okay, so let's try to simplify it then. What do we have from that stage? So -2 root of 3 multiplied by -2 root of 3. So 2 times 2 is 4. Then root of 3 by 3 is 3. So basically we are expected to have a 12 there. So we have 12 plus, that is going to be a 1, and we have the root of 12 plus 1. So basically if you add 12 plus 1, what do you basically get to have? So this is going to be the root of 13, and that's what we have in this case. Okay. So we've looked at the issue of dealing with the absolute value as well as how to plot it. So from the concept that we have in mind, let's get to the issue of the complex plane. So on our complex plane, how we're plotting we're saying the y-axis is basically the imaginary part, then the x-axis is basically the real part. So how do you get to plot a complex number? So we've said when we have a complex number a plus ib, assuming in this case both a and b are positive, the complex number is expected to fall in this quadrant. Okay, so let's try to draw a line there. We see how it's going to be. So that is where a complex number is. So note that this complex number has got this part, which is of course representing the imaginary part. So the imaginary part is being represented by b. Then I'll use a different color representing the real part. Okay, so that will be our a. So we've plotted a complex number on the complex plane. So basically this form that we have, this is called the rectangular form of the complex number. So how do we get to take it to what we are calling the polar form? So the polar form basically is going to be a form where you get to see a complex number being equal to r. Then what you get to have is of course cos theta, then plus I sin theta. So this is kind of something that is derived from the basic concept that we have. So realizing the fact that basically your r there is basically your absolute value. So put our r there to represent the absolute value of that complex number. So your r is the absolute value. And the basic concept, if you get to look at our vectors, we know that taking consideration that angle there, let us say the angle there is theta, and if we have there our angle to be theta, how is it going to be? So trying to find b from the trigonometric ratios, you are going to see that basically b is actually the opposite of that angle. So it's basically sine of that angle, the opposite is b, then we know that the hypotenuse is basically the absolute value r. So if you try to make b the subject, you find that basically your b is going to be a product of r with sine theta on the left. Then the same concept can be applied to our a. So a is basically adjacent to the angle theta. So basically we get to use cosine for that. So you can say cos theta is going to be, the adjacent side is a, of course the hypotenuse remains the absolute value r there. So if you make a to be a subject, it's going to be what? It's going to be r cos theta. Okay. So now, not forgetting that basically when you talk about the issue of b, we are saying b basically has got what we are calling what? The imaginary part. So it having an imaginary part, we're supposed to include the I there. Of course, let's not show that for now. So we have our a and our b. So if you try to substitute in this part, that is what we're going to have in the rectangular form. So let me try to remove this for now. We see what we're going to have. So what we're going to have as our complex number, given that our a is r cos theta, then our b is r sin theta. Of course, there is an I attached to that form, so we put an I there. Okay, so if you get to factorize your r there, what you're going to have is what I wrote before. So that is how basically you get to, so I'll put the I as a coefficient. So that's how you get to find or convert from rectangular form to polar form under complex numbers. So the other concept that we have to understand is how do we get to find the argumentative, or the argument are basically theta there. How do you get to find it? So just like we know, if we get back to a diagram there, a complex number is there. okay, at that point, and this is our B, this is our A, and that is our theta. So basically the way it's going to work out is the fact that we know, okay, if you know your A and you know your B, basically your tan inverse of that is basically what is going to give us what? So it's basically going to be B over A. So you'll be able to find the angle of theta, and you plug in this equation. Then what you're going to have is basically the expression of the complex number in polar form. We have a number of practice problems that we're going to look at. So to start with, plot the complex number that in the complex plane and then write it in its polar form. So this is just like trying to apply the concept that I was just from talking about. So basically, if you look at the complex plane, basically you expect to have the x and the y-axis. Of course, in this part we understand that as you talk about the y-axis, you're talking about the imaginary part, and as you talk about the x-axis, you're talking about the real part. So basically, z is equal to the negative root of 3. So that is representing the real part. So basically, it's supposed to be somewhere this side on the negative part. So assuming at that point, that's where we have the roots of negative root of 3. Then you have I somewhere there. So if you get to plot it there, you have it there. So that complex number there. So let me draw a line. Okay. So that's what we have. So now we'll say, okay, the imaginary part is going to be represented by B. Then this is your M. So what complex number that we have is basically in the form of A plus IB. Okay. So now taking into consideration the angle there to be theta, so we're able to convert that to polar form. So how do we get to find A from a trigonometric ratios? So what we are saying is A is basically going to be what? So A is the x part. So that is basically going to be what? So let's say that is the R in this case should be, of course, the absolute value of the hypotenuse. So your A is going to be R cos theta, then your B is going to be R sin theta. So basically, if you get to put that there, so do we know the value of R? We don't know. So how do we get to find it? So we know that the value of R is basically the absolute value of a complex number that you have in that form. So we understand that in this case our A is negative root of 3, then our B is basically the coefficient of I, which is just 1. So therefore our absolute value in this case is going to be the negative root of 3 squared plus 1 squared. So in such a case, negative root of 3 multiplied by negative root of 3 is going to be a positive 3 plus a 1. So basically we're going to have a root of 4, which is going to be a 2. So we have our value of R there to be 2. So we can write R is equal to 2. We have to find the value of theta now. So we said angle theta is going to be tan inverse of B over A. So in this case, what is our B? So our B is a 1. What is our A? It's a negative root of 3. So whenever it is negative, you can consider it to be positive. Okay. So taking an assumption it is positive. So 1 divided by root of 3, that is basically going to be a special angle that you may know. Okay. So basically the angle there is 30. So our reference angle is 30 because we just considered the sign to be a positive. But then in which quadrant is this complex number? It's in the second quadrant. So it's obviously supposed to be less than 180. So we can subtract from 180. And we basically get to find that our angle is basically going to be 180 minus 30, which is just going to be 150. Because the equivalence of 30 in the second quadrant is 150. Okay, so we have 150 there as our angle. And knowing that if you get to plug in the values that we have for A and our B, yeah, boy, that is basically going to be your polar form. So where there is A, if we put R cos theta, and where there is B, we get to put this. It's going to be I R sin what? Sin theta. And you plug in the values that you have. So for R we said it's 2, and it's basically common, so you can factorize it. So we have a 2. You can write that bit on top. So we have a 2, then open brackets cos. What angle do we have? Our angle that we have is cos 150. Then what we have is So we say I, then sine 150 again. So we can leave the answer like that because the question says leave it in polar form. So if at all we wanted our answer to be in a plus ib form, would basically get to punch on the calculator and be able to determine the exact values of cos 150 and also 150 there. Okay, so we have another question. Yeah, so z is basically equivalent to that. Now in this case, what I want us to do is basically get this is, of course we understand this is polar form, so we want to take it now to the a plus ib form, which is basically called the rectangular form. How do we get to do that kind of a conversion? So basically what I want you to understand is all you have to do in this case is just a matter of you trying to now evaluate what you have. So try to get your calculator, take your angles to radians. Then basically when you look at cos, of course cos theta over 3, in terms of if you try to convert the angle to spatial angles, you find that's going to be a case which is basically going to be just 1 over 2. So cos that is a spatial angle, is 1 over 2. Then you have got your I there, sine what? So sine 60 basically is what? Or sine pi over 3 is basically what? It's basically the root of 3 over 2. At that point you can multiply, so you have 5 over 2 plus, so when you have 5 root of 3 over 2 I. So we've basically expressed it in the form of a plus ib in this case. So basically when you have it in polar form, it's very easy for you to take it to the other form of the rectangular form, which is just a matter of you just trying to open the brackets and simplify it. Okay, so now we've understood how to change from the rectangular form to polar form. So there are some mathematical operations that we basically have to understand as we get to talk about the polar form. How do you get to how to multiply? How do you get to divide? Okay, so let's try to understand how we basically get to do that. So now in this case I'll take two assumptions. Yeah, let's say that our complex number 1 in polar form is in the basic form that we've talked about. So let's say r, then we say cos theta plus I sine theta. Then we also say, okay, let our second complex number also in polar form. So I'll use different letters. Yeah. So I'll say maybe let's let this be t. Then I'll say cos. So instead of using the theta, I can use a different sign to show that. Basically, let me even use a different color so that you're able to see clearly. So cos, I'll use a different sign there. Just I sine that again. So we have two different complex numbers, both written in polar form with different absolute values around t. So now, assuming they ask you to say multiply these two or find the product of these two complex numbers, how basically do you get to approach such a question? What are you expected to do? So basically when you are trying to multiply two complex numbers, first of all, what you need to understand in polar form, let's just look at the product. So multiply the absolute values. In this case we have r and t, so we have r and t. Then the other thing that is going to change is you maintain your cos there, then you just add their angles. So from the first case what we have is theta, then I'll also get the other angle from the other complex number. Then again I'll say plus I sine, I'll maintain that, then I'll just add the angles again. I'll just add the theta with that angle there. So theta. So let me start with theta, then get to add the other part. So that is the basic idea. Let me just show that a bit down so that you clearly see it. So what I'm trying to say is the other side is just going to be I sine. So you just gets to add the angles as well. So that is basically the way what you get to do when you're dealing with multiplication of these complex numbers in polar form. You just get to multiply the absolute values and gets to add the angles that you have. Then the other thing that is important, also being able to determine the quotient or being able to divide these complex numbers. How do you get to do that basically? So assuming we are taught to find the quotient of z1 to z2, so you're trying to divide. So as you might guess there, when it comes to the absolute values r and t, we're going to divide. Okay. So then I'll start with the first one on top, z1, which has got cos theta So here what you're going to do, what is going to happen is we're going to be subtracting the angles. Okay, so plus we now have I sine, so we'll do the same there, we'll have to subtract. Okay, so instead of adding this time around for division or determining the quotient, we just get to divide the absolute values, then get to subtract the angles that we have been given. Okay, so now from the basic operations that we've learned under the polar form, they are going to help us come up with what we call the moivre's theorem. So basically, I'll take two assumptions. Let's say that we are talking about z1. Okay, in polar form, it's basically r when we say cos theta plus I sine what? Sine theta. That is basically the form of the angle that we have in such a case. So now I also say that, okay, let z2 be the same as well. It will basically have the exact thing there. So we have that. Okay, it's basically the same, the angle is the same, the absolute value is also what? Is also the same. Now let's say we get to look at the product of these two complex numbers, and of course when you say z1 is being multiplied by z2, basically what you get to have. So from our rules that we're trying to say under the conventions, from the mathematical operations under polar form, we say that when you are multiplying two complex numbers, you get to multiply their absolute values. So in this case, what we have r multiplied by r, so it will be r squared. Then for the angles, what we get to, we said we get to look at the factors. So okay, we get to add. So theta plus theta is going to be 2 theta. Then the same is going to be applied the other side to theta because they are identical. So that's what we have in such a case. So remember that we can take, so this is like z1 basically is actually in the form, rectangular form of a plus ib. So it's like we are multiplying it by itself. So we have a plus ib. It's kind of squared twice, and it's actually equivalent to r squared cos 2 theta plus I sine 2 theta. So what are we trying to say here? So here the point that we're trying to make is we had z, and this z1 is actually a complex number a plus ib. So after multiplying it by itself, it means a plus ib in brackets squared. So it's basically equivalent to this from the mathematical operations that we've done. So from this very relationship that we have, we can notice that what we've only done to the polar form of a complex number is the fact that, okay, we know that a plus ib in rectangular form is basically equal to r cos theta plus I sine theta. Of course, this is in polar form. So now, after putting a power of 2 there, what have we noticed? We've noticed that even the r is also become squared, then the angles are going to be 2, 2, just like that. So this is basically what we get to say the moivre's theorem. The fact that if you raise a complex number in rectangular form to any power n, you just get to become that the angle will be multiplied by n on both sides. So basically that is what we call the moivre's theorem. It's very applicable when they ask you to find the roots of complex numbers and other things that we're going to see as we get to look at different practice questions. Alright, so from mathematical operations and the de Moivre's theorem, let's try to look at these questions now. So find the product of the complex number z1 is equal to that, z2 is equal to that, leave your answer in polar form. So what did you say about the product? So we said whenever you're dealing at the products, so in this case we have z1 being multiplied by z2, just multiply the absolute values. So 3 by 4 is a 12. We understand that. The other stage you said you get for cosine, then what do you get to do about the angles when you are multiplying? You get to add. So we have 32 in the first case plus 61 in the second case plus I sine. So the same is going to apply for sine. We're supposed to add the angles that we have. So we have 32 again and 61. Of course, these are in degrees. Okay, so that's what we have as a product. So z1 applied by z2 is going to be 12. So 32 plus 61 is basically what? 93. So we have cos 93 plus I sine 93. So basically this is what you have as your product in polar form. Of course, if they want it in the rectangular form, you got to simplify this and, you know, get to simplify it further. You'll be able to get your solution in the rectangular form. Okay, the next question says find the quotient of the complex numbers. Z1 is equal to that and Z2 is equivalent to that. Leave your answer in polar form. So the quotient. So a quotient of Z1 to Z2, we made a point to say the absolute values are supposed to be divided. In this case, we have 12 being divided by the 3 from the other complex number there. Then the other thing that we said is for the angles, what you get to do, you ought to subtract. So we'll say 84 there in the first case, minus 35. So this is going to be plus high sine. The other side we do the same. We have an angle of 84 minus 35. Okay, so 12 divided by 3 is basically a 4. Then 84 subtract 35 is basically 49. So we have cos 49 plus I sine 49. So this is basically our quotient of Z1 to Z2 in polar form. Use the moivre's theorem to find the fifth power of a complex number Z2, or Z is equal to 2 cos 24 plus I sine 24. So when they say the fifth power, so in this case what we've been told is we've been told our Z, or our complex number, is equal to 2 cos 24 degrees plus I sine 24 degrees. So when you say fifth power, you're trying to raise it to the power 5 in such a case. And how does that apply? So if you go back to the moivre's theorem, what are we being taught first of all? So what we're being taught is the fact that when you have Z being raised to any power n, basically this is going to apply to the absolute value, and also what you have, the angle is going to be multiplied by the same power. Okay, so this is basically what the summary of the moivre's theorem. That's what we're trying to say. That's the point that we are making. Okay, so now in this case we're trying to raise it to the power 5. So the same is going to be applicable. It's going to apply. So basically look at the values that we have. So if we raise that to the power 5, it will apply to the R. So put it to the power 5, meaning that even the angles are supposed to be multiplied by 5. That's what the moivre's theorem tells us to say, if you look at this. So let's try to simplify that then. So of Z being equal to the power 5, then our absolute value in this case is 2 to the power 5. So of course, our n is basically what? Our n is basically 5 in this case. So our angle theta is 24 plus I sine 5 again by 24. That's what we have in this case. So at this point, we should be able to find our Z to the fifth power. So we basically understand that 2 to the power 5 is basically a 32. We appreciate that. So 5 being multiplied by 24 is basically going to be a 120. So we have, of course, 120 degrees plus I sine 120 degrees. So that's what we have. So now they want us to express our solution in rectangular form, so we want to simplify it even further than what we have in that case. Okay. So what do we have? So we have Z is equal to 32. So what is cos 120? Is it a special angle? Okay. So cos 120 is not basically a special angle. So the only way that you can simplify it further is just by trying to work around with what you have. So in such a case, it would be a requirement for you to use a calculator if you want to simplify it further than what we have. Okay. So the other way that you can express cos 120 in terms of the special angles, we can express it to be basically the root of 3 over 2. That's for cos 120. Then sine 120 can be expressed to be just 1 over 2. Okay, so you can say 1 over 2. So at that point, if you get to multiply what we have, 32 outside there, being multiplied by that, what are you going to have? So you're basically going to have 32 being multiplied by the root of 3 over 2, which is just going to be like a 16. So you have something like a 16. Then you have the root of 3 plus 16i. So this is the way that you get to express it in the, what we're calling the rectangular form. Okay. So this is how applicable the moivre's theorem is. We still have 2 more questions. Use the moivre's theorem to find the third power of the complex number z is equal to that. Alright. So you have z being equal to 2 plus 2i. Then what have you been told? You've been told to find the third power. So how do you get to find the third power? You get raised to the power 3. So the moivre's theorem, what we're trying to say is this. So assuming that's what you have, so whatever you raise it to, so that would be power 3, that would be by 3 by 3. That's what the moivre's theorem is telling us. So now if you look at the angle that we have in this case, or basically look at the complex number that we have, it's basically in the form of L plus IB. So we want to make sure we have our absolute value R as well as our angle theta. So let's try to do that. So our absolute value in this case is going to be the root of 2 squared plus 2 squared. So basically, what is 2 squared plus 2 squared? So you have a 4 plus a 4, which is going to be the root of 8. Okay? So we also know that 8 is basically 2 by 4, which can be now the root of 2, then a 2 outside. So we can even say 2 root what? 2. So our R is 2 root 2. So we have our absolute value in this case. We can move. What else do we need to find? We need to find the angle theta. So our theta is going to be equal to, we say it's tan inverse of what? B over A. So what is our B in this case? So our B is the coefficient of the imaginary part, which is a 2. So we have 2. So basically it's going to be tan inverse of just a 1. In radians, the angle that can give us pi of, that can give us that can give us 1 is basically pi over 4. So our theta is equal to pi over 4. Okay. So if you're looking at this in terms of degrees, what angle can give you pi over 4? It's 45. So 45 is also, if you are working with degrees, you can work with 45. But in this case, I'll work with radians. So pi over 4. So we have our angle, we do have also our absolute value. So we should be able to find now what we have using the moivre's theorem. So Z3, so our R value is basically pi over 4. Sorry, it's 2 root of 2. That is our absolute value. So to the power 3 plus, open brackets, we have cos 3 pi over 4 plus I sine the same 3 pi over 4. Alright, so we do have it in that simplified form now. What would you want to do now? Let's try to simplify it further and want to find it in the form of L plus bi. So 2 root of 2 being multiplied by 3 times, basically what do you get to have? So we have 2 root of 2 by 2 root of 2. So in the first case, 2 times 2 is a 4. Root of 2 times root of 2 is a 2. So you have a 8. So now you have your 8 being multiplied by another 2 root of 2. It's basically going to be 16, then root of 2. So we simplify the first part. So we do have 16 root of 2, open brackets. So when you multiply cos 3 pi over 4, it's going to be what? It's going to be cos 3 pi over 4. Then the same will apply to the other part, I sine 3 pi over 4. So we've just like multiplied the 3 by the angle that was initially there. Okay. So at this point we understand that what we have are spatial angles that are determinable. Okay. So of course, if you look at 3 pi over 4 in degrees, it's basically supposed to be equivalent to what? To a certain angle for it should be 135. Okay, so now what you're going to have in this case is you now have, so remember it is our 16, so 16 root of 2 open brackets. So what is cos 3 pi over 4? What is that equivalent to? Cos 3 pi over 4. So you can grab your calculator. So it's basically equivalent to root of 2 over a 2 plus the other part we expect the same, root of 2 over 2. So if you would want to understand this, basically root of 2 over a 2, if you multiply it by a 2, root of 2, or let's say, yeah, root of 2, it's going to be 2. Then you basically have, it turns out to be 1 over root of 2. So basically that's the actual angle that you get to have. It's 1 over root 2. Okay. So at this point, if you get to open the brackets, what are you going to have? So if you multiply, basically what's going to be happening is what is going to be on top is going to be cancelling out. So what you're going to have is 16. Then you have a 2 there, which is going to divide by the 2. So it's just going to be a negative. Then for the other part, you just have like 16i. The root of 2 and the root of 2 give us a 2, which is going to be divided by the 2 on the denominator part. So this is basically what is going to be equivalent to the third power. Find the complex cube roots of that. So we've talked about finding the powers, raising them to r powers. Now, how do you get to find the roots? Working with the same principle of the moivre theorem. So when they ask you to find the roots, what I want you to understand is the fact that you can find up to even 4 solutions. It's very, very possible. Okay. So how do you get to approach a question? So the way we're going to approach our question is in this case. So if you have your complex number z is equal to r cos theta plus I sin theta. So that is in polar form. So let's say you have 4 there and you want to find the 4th root, or let's work with what we have, third. Now you want to find the 3rd root of this side. So it's going to be, your r is going to be raised to 1/3. Even everything else this side is going to be raised to 1/3. Okay. So the concept of the basic idea is going to be, for the first possible solution, of course, from the moivre theorem, we understand that it's going to be what? It's going to be r to the power n, in this case, which is the 3rd root. Then the angle is going to be multiplied by the same, so cos. So 1 over 3 multiplied by the theta is going to be theta over 3 plus I sine theta over what? 3. So that is the first possible solution. But then the other thing that we have to understand is the angle that can give you a certain value. Let's say if you have a possible solution being in the first quadrant there. I'll give an example of sine 30. So we understand that sine 30 is equal to 1 over 2. So somebody else may also say, okay, you are saying your angle theta is 30. Me, I'll tell you, how about I take 1 round, and basically I'll take 360. So plus another 30 there. It's basically going to be 390. And if you get to punch it as well, it will also give you what? It's basically 1 over 2. So the same applies even as you get to find the roots under the complex numbers. So the generalized form of finding the roots is basically going to be r to the power n, then cos. So we are going to make a point to say the angle theta that you have, so it's going to be, now we add the number of rotations that you make. So you can say 2 pi to generalize that. Then this can be multiplied by how many times you rotate. Okay, so that's what you're going to have, plus I sine the actual angle theta that you have, plus k by the number of rotations. So this is in radians. So in terms of degrees where they have put 2 pi, you can just put 360 to demonstrate or show how many times it rotates, plus the original angle. Okay. So let's get back to what we have in this case. So looking at what we have in this case, so looking at the fact that okay, so I'll remove n in this case because I've not shown it, because the moment I show the n is also going to be applicable on the right hand side. Okay, so now let's say our z is raised to the power 1 over 3. So what is going to happen is, from the moivre theorem, we understand the fact that your r is supposed to be raised to the same power. In this case, what we have is 8. So it's basically going to be 8. So 8. Then we have 1 over 3 as a third root. So we have cos. So what we have is our theta there. So what theta do we have? We have 60 in this case. So say 60 plus, I'll say k. Then our angle is just 2 theta, 2 pi there, plus I sine. So 60 plus k 2 pi as well. So that is going to be applicable as well. So now at this point, this is just a generalized form of our solution. So the third root of 8 is basically a 2. So that is going to be a 2. So now, the first possible solution that we can have is when k is equal to 0. If you let k be equal to 0, your z1 is basically going to be equivalent to what? So it's going to be 2. So meaning that the rotations are cancelled out. It's like the basic first possible solution. Okay, so what you're going to have is without rotation. So it's going to be 2. Then what you have is cos 60 plus I sine 60 as well. So all the parts with k have been eliminated. And we can say that is basically our first possible solution. But remember, what are we trying to find? We're trying to find the third root. So the third root is going to be very applicable, just as much as we indicated it to the 8 there. Remember we said we're trying to find the third root. So there was initially 8 this side. So the third root of that, the moment we find the third root of that, we're supposed to apply it this side as well. So it will be there. You multiply it by every angle and every angle, giving us our possible solution to be basically 2, then cos. So we have cos 20 plus I sine 20. Okay. So for our second possible solution, is when k is equal to, so to avoid the issue of forgetting, let me put n there as well. N will now entail the angle that you're dealing with. Okay, let me put 8 there, then n. So in this case, we're trying to find the cube root. So a cube root is 1 over 3. So for our second value, we are saying when k is equal to 1. So k is equal to 1. Remember, our n is still going to be the third root there. So for our z2, it's going to be 8 to 1/3, which is to say 2. Then in the brackets you have cos. So we have a 60. We're trying to divide by a 3 there. So it's going to be a 20. Our k is a 1. So it's just going to be plus. So so we've used the mixture of degrees with radians. So let's take that to degrees so that we work with what we have. So plus 360 to show that we've done one rotation, plus I sine, again that is 20 plus 360. So we have 2. So cos, that is going to be cos what? 60 plus 20 is what? So a 380 plus I sine 360 or 380, sorry. Okay, so that's what we're saying as our other possible solution in this case, because basically what we're trying to say is the fact that, so which one is coming first here? So let me just correct that mistake there. Okay, so n is basically supposed to be multiplied with everything else in the brackets, because n, let me use a different color for that. So we have n, then we also have sine n again, then we have 60 plus that. So meaning that you're supposed to divide by 3 after doing the computations. Let me make a full summary of it all. So what I'm trying to say, when you're finding a root, your complex number is in this form is actually that z is equal to, so we are saying r, then we have cos theta plus I sine what? Sine theta. That's a general form that we have. So we're saying for our root, when finding a root, it's basically going to be r to the power n, then cos theta is going to be added with the number of rotations that you get to take. If it's in degrees, we can say 360. Of course, so we don't know how many times you're going to rotate. We just say rotate k times. So this is supposed to be divided now by n. So the same applies on the other side, I sine. So whatever I've indicated there is supposed to be shown the other side. So for a second possible value, we are saying our k is equal to 1. So therefore our z2 is going to be, our r in this case is 8. 8 to the third root is 2. So we have cos. What pi do we have? So we have 60 plus, so k is equal to 1. So divided by 3. So whatever we're going to have is going to apply to the sine as well at that point. So basically 60 plus 360. 60 plus 360 is 420 divided by 3. So it's 140. So therefore our possible z2 value is going to be 2. Then we have cos 140 degrees plus I sine 140 degrees. So this is in brackets, of course. So these are the possible roots, cube roots of that complex number. And this is how applicable the Moivre's theorem is. So thank you very much for making it to the end of this video. I just hope that you now are able to do with some further computations on the Moivre's theorem.